Hi, my name is Emily. I'm a researcher in the Space Rendezvous Lab at Stanford, and I'll be presenting today on a very long title here called Removing Ambiguities in Concurrent Monocular Single-Shot Spacecraft Shape and Pose Estimation Using a Deep Neural Network. To give a sort of TLDR on that title, the idea here is we want to concurrently estimate the shape and pose of a spacecraft that we are rendezvousing with, while avoiding certain ambiguities in the definitions of the shape and the pose that lead to poor solutions. And I'll get into what that means in the course of the presentation. So to outline what I'll be talking about through this presentation, I'll introduce sort of the motivation for this problem that I'm presenting and what problem I really want to be solving here, some of the prior work that's in this area, and then I'll dive into the methodology of how that we've been approaching this problem. So I'll introduce an application here, which is a particular convolutional neural network that estimates shape and pose of a target spacecraft. I'll talk a little bit about some of the challenges in concurrent shape and pose estimation, and then I'll talk about two different approaches to trying to solve some of those challenges. One of them I'm calling an ambiguity-aware convolutional neural network and an ambiguity-free convolutional neural network. And then I'll finish by summarizing results and talking about some of the conclusions from this work and the future work that we see coming out of it. So to motivate the problem here, I don't think I need to explain this too much to anyone in this room, but there's a huge proliferation of space missions, particularly in certain orbits like GEO and LEO, especially as proliferated space missions become more and more popular. And this often leads to a lot of space debris that can clog up these really popular orbits and pose a lot of hazards to the important spacecraft that are operating there today. So there's been a lot of interest in recent years in autonomous space debris inspection and removal. This type of paradigm would enable us to remove whatever uncontrolled junk might be up in these orbits that are posing hazards to the spacecraft that we operate, and move them to a safe orbit or deorbit them safely. But this is kind of a complex process. Technologies are very much still in development. And one of the parts of this process is in the very beginning of that GNC pipeline, we have to be able to navigate safely around these target space objects in order to characterize them, understand how they are moving in space, what the hazards or characteristics on the spacecraft are before we can do any kind of guidance, control, docking maneuvers around those spacecraft. And so specifically, we need to characterize the target's shape and pose in order to carry out this type of mission. So the goal of my work is to enable us to rapidly estimate the pose and shape of an unknown and uncooperative target spacecraft using a single monocular image. I emphasize monocular in that we want this to be able to operate on a system that maybe is low budget, might lack redundancy, doesn't necessarily have the benefit of using something like stereophotography or laser ranging that a more expensive mission might have. We want this to really enable this kind of mission to be carried out at a lower cost or with maybe a case where there's less redundancy than we would love to have. So there's plenty of prior work that is related to this topic of characterizing an unknown space object in orbit. A lot of it is borrowing sort of from the conventional computer vision world. Obviously, there's a lot of pose estimation and shape estimation work in computer vision at large. But applying it to the space world can be a little challenging at times. So sort of on the left here, I talk about some of the approaches that we've been seeing in a lot of work over the past decades. And this is what I'm calling conventional computer vision. So examples of this are the commonly known SLAM, or we like to talk about sort of a superset of SLAM called simultaneous navigation and characterization, or SNAC. And this allows you to sort of sequentially refine estimates of the pose and the shape of the space object, perhaps other characteristics like the moment of inertia or other characteristics that might be of interest to you. Now, the challenge of using this in a space application, while it has been demonstrated before, they can be challenging in that it requires you to use a batch of images to initialize those estimates. And they need to have sort of sufficient diversity of geometry, and you need to be able to overcome challenges that are inherent to space imagery, like really harsh lighting, camera lens flares or lighting fluctuations, as well as just kind of a generally low signal-to-noise environment and a low bandwidth of images. So there's been plenty of work to try to move beyond this paradigm towards something that can kind of handle this environment a little bit better. A very popular topic in computer vision right now is novel view synthesis. Two methods of this that we hear a lot about right now are Gaussian splatting and NeRFs. These are both methods to create these high-fidelity representations of a scene so that you can render new views of that scene that are realistic and high fidelity from different view angles than whatever you might actually be looking at the moment. When you have a well-constructed novel view synthesis scene, you can determine the pose for a new image by minimizing across view angles based on some input image. So in theory, this is a way to determine the pose of an image, but first you have to construct your model of the scene, i.e. the shape. And to do that, to construct that initial model, you need to know the pose. And so it has, this issue that we saw in the conventional realm where you need a batch of images. In addition, you need to have known poses, so that's an even bigger challenge. So to solve this problem and make both of those missions a bit more tractable in space or a bit faster to initialize in these kinds of applications, there's been some research on these single-shot deep learning-based methods for creating an instantaneous estimate of the shape and the pose based on an input image. And these have shown some success so far, but they're not super developed yet. So I'll point out one example here was introduced last year, and it's sort of a Gaussian splatting based model that sort of represents the spacecraft as an assembly of Gaussian splats. And then in theory, one could go in there and determine pose based on that model. In practice, one side of the model tends to look really good and one side of the model looks not so promising and probably wouldn't help you get the pose. And then there's another piece of work that came out of my lab, which is a convolutional neural network that estimates the shape as a representation of these shape primitives called superquadrics, which I'll talk about in a few minutes. This one performed decently well on spacecraft that it had seen before during training, but really struggled with unseen spacecraft, and the rotation errors were really high throughout. So clearly there's still some challenges in this paradigm, but if we can get this paradigm of single-shot initialization of a shape and pose estimate to work, that allows us to initialize these other methods much more quickly than they're currently done today and can allow a much quicker convergence of our navigation pipeline towards being able to carry out whatever the subsequent mission is. So I'll talk a little bit now about the architecture of this CNN. I'm going to be using this sort of as a use case to discuss the concepts that I'm talking about in my presentation today. So the convolutional neural network that was introduced in my lab last year here for shape and pose estimation estimates the shape, as I said, as an assembly of what we call superquadrics shape primitives. And these are these shapes that are parameterized by a fairly small group of numbers. Here you can see we have a size and shape parameters, as well as translation and rotation from the body axis of the target, along with some additional tapering parameters that allow you to kind of add more shape options into the list of shapes you can make. So essentially, these are just arranged relative to the body axis of your target. And essentially, these few parameters are used to, you can input these parameters into functions that allow you to sample points from the surface of this shape primitive or points from the interior of the shape primitive. And so in essence, it represents this shape compactly with a few primitives. It also estimates a rotation and a translation. Translation is just literally the translation vector. The rotation is directly it's estimated as a 6D rotation vector because this is a continuous representation of rotation that's easier for a neural network to learn. But we convert it to the more conventional 3x3 DCM for whatever operations we're going to do at the downstream so that we can use it in an intuitive way. So to train this neural network, the method that is sort of used in the default implementation is this weighted sum of different sort of component loss functions. So you can see we have a rotation loss, translation loss, chamfer loss, reprojection loss, and regularization losses. So I'm going to show kind of the important ones here and talk a little bit about them. So the rotation loss is simply the magnitude of the rotation, the sort of absolute rotation between the estimated rotation matrix and the ground truth rotation matrix. And so obviously it's going to penalize a higher divergence of that rotation estimate. Translation estimate, similarly, is just sort of a normalized difference in the estimated translation and the actual translation. Chamfer distance, this is a measure of, essentially a measure of distance between two sets of points that can represent how close one set of point is to, reproducing the other set of points. So the way that we use this is S1 in this case would be the set of points sampled from the surfaces of our superquadrics primitives. So this is representing the surface of the spacecraft. And then S2 would be sampled from a 3D mesh model of the reference truth 3D mesh model of the spacecraft at hand. And then you're sort of minimizing points that, a selection of points that minimize the L2 norm, squared L2 norm between each given point and the points in the other point cloud. And this is a pretty commonly seen loss in computer vision, shape reconstruction applications. We also have a reprojection loss. This is essentially a comparison of the binary mask that shows what part of the image frame you expect to be occupied by the target spacecraft based on your estimate of the shape and the pose, compared to the actual binary mask of what the ground truth data says is occupied by the target spacecraft. So essentially, we're just doing a mean squared error between those two images. Finally, the regularizations are not really focused on here, but essentially these just try to discourage the network from overlapping the primitives too heavily or tapering them too extremely. We want to try to prioritize it to use each of those primitives, and we want to encourage it to make boxy or cylindrical shapes because that's what we typically see on spacecraft. This network has been trained on this data set that was published with the original implementation of the network, the SPEAR data set. It provides these unit-scaled 3D models of 64 different spacecraft. It has 1,000 simulated, somewhat realistic space-based images of those 64 spacecraft. So the way that we use this during training is we split it into a training set and a validation set and a testing set. 57 spacecraft are used for training. 800 of those images are used in the training process, and then we run it for many epochs. The remaining 200 images of those 57 spacecraft, we put those in the validation data set. So the validation data set is, in essence, it's a set of unseen images of spacecraft that were seen during training. So they're familiar spacecraft, new pictures. On the other hand, the test set, they're the images of the spacecraft that were never seen during training. So this is really how we can test how it can abstract or generalize to completely new geometries of satellites. And then these have the additional data that's needed to provide those labels that we use during training. So it has the binary masks, it has the reference truth poses. And like I said, it has this mesh model that we can use to sample the surface points and the occupancy points as needed. You'll note I point out that they're unit-scaled 3D models. You might have been wondering how on earth we can get translation from a monocular system, since that's famously not really possible. So picture our translation estimates are essentially sort of a scaled translation estimate based on the 3D model being scaled down. So you can picture it sort of being relative to the size of the spacecraft itself. And then in terms of the metrics that we were evaluating the network on at the end, these are rotation error and translation error. These are the same computations as in the loss. It's just the magnitude of the rotation error, the rotation between the estimate and the ground truth, and the translation between those two things. And then we use L1 chamfer distance instead of L2 chamfer distance in the evaluation as well. This is a fairly conventional choice in a lot of computer vision, shape reconstruction applications. And it's a way to make sure that we're not just overfitting to one single metric in our training. So as I mentioned before, the implementation that my colleague Jeff Park introduced last year was very strong at memorizing the spacecraft that were in the training data set, but struggled a lot more with the testing data set, and it struggled a lot with rotation estimates across the board. And so we kind of took a bit of a deep dive into why that might be happening and why it seemed to be struggling a lot with this problem. So we should talk a little bit about what it means to concurrently estimate the shape and pose of different objects. When you estimate the pose of something, you're essentially saying, I want to estimate what the transformation from my reference frame is, my body axis frame, to that body axis frame of that object. So typically that's pretty easy to define what that axis frame should be on an object, because a lot of objects, like this chair, for instance, they have what we call a canonical pose. That means that we can kind of all agree on what the front of the chair is and what the top of the chair is and what the right and left side of the chair is. So determining a pose is easy because we can easily assign a body axis based on those definitions. But what about when an object doesn't have a canonical pose? So a lot of spacecraft are going to have really diverse sensor configurations. They might not always be pointing in the same attitude throughout their mission. They might actuate the solar panels. They might even be rotationally symmetric. And this makes it a lot harder to generalize across the board some sort of system for deciding what the front, back, side of a spacecraft is. So what if we used a different rule to do this? What if we assigned it based on sort of the principal axes, or what dimension is longest on the spacecraft? This is essentially what the SPEAR data set does. It takes the longest dimensions of the spacecraft, sets that as the first body axis. The next longest dimension is the second body axis, and then the third is the cross of those two. That seems like a decent rule, right? It's sort of based on the geometry of the satellite. You can always figure out what the geometry of your satellite is. But unfortunately, this is not a unique formulation. There's 4 different permutations of those body axis triads based on the dimensions of that satellite. And so this wasn't really accounted for in the initial implementation, and our theory was that this may have been contributing to some of the challenges, particularly in estimating the rotation, but it may have also led to challenges in estimating the shape of the spacecraft as well. So I'll introduce one of the methods that we implemented to try to address these ambiguities in the body axis definition. The goal here was to remove any unfair penalties that we were giving to the network during training, where we might have been comparing an estimated rotation to a ground truth rotation that was based on a different understanding of what those body axes are. Similarly, we don't want to penalize sort of a fairly accurate representation of the shape that just is flipped around by 180 degrees. Because while the network does a good job at sort of aligning the shapes along those sort of principal dimensions, it doesn't have a way to know which one of those permutations was used in the ground truth data. So the essential process for this is fairly straightforward. We permute the rotation estimate and the group of points that represents the sampled from the surface that we use in the chamfer loss. We permute each of those by those 4 different matrices that allow us to have those 180-degree permutations along each principal axis. And then when we calculate the rotation loss and the chamfer loss, we simply take the minimum across those 4 permutations and keep whichever one is lowest. And the theory was that this would allow us to sort of train it to choose some orientation that still follows the rule, and it would choose a combination of the rotation and the shape estimate that would combine to give a good reprojection estimate without being penalized sort of unfairly. And so I have some results here. I'll summarize these at the end, but I wanted to give a few intermediate results here. The sort of big picture that you can see here is we did see improvements to both the rotation estimates and the shape estimates from this sort of ambiguity-aware network implementation. Specifically, the rotation estimate for the validation set improved by a small amount, but it improved by a more significant about 10 degrees of error on the test set. However, it's still kind of high. It's about 50 degrees. More significantly, we see an improvement of around 20% of the error magnitude in the test set for the chamfer distance estimate. So we see a much stronger performance in reconstruction than we were seeing previously in the baseline case. And I've included an example here just to kind of show some of this performance improvement that we saw. So this is a particular case where we have a satellite that has sort of one long extended boom. The baseline set, as you can see, has kind of overfit itself to these spacecraft that have 2 extended solar panels, and so it really struggled to identify that there was a single boom extended from this. But the ambiguity-aware estimate did correctly identify that that was the case. And so it had while it lacks a bit of the detail on the surface, it did have a stronger reconstruction of the overall shape of the spacecraft. Similarly, in this test spacecraft from the test set, we can see, again, I think the baseline really struggles to generalize to these different classes of geometry. It really wants things to converge to 2 panels. The ambiguity-aware one struggles a little bit still to understand that there are 2 panels, but it does a much stronger job at creating one that's much longer than the other one. It is a better reconstruction of the shape at hand. But as I pointed out, our rotation error is still really high. It's about 50 degrees. If I were to use this to actually initialize some SLAM or SNAC pipeline or Gaussian splatting, as we know, that 50 degrees of error is going to add a huge amount of spatial error in where those points are. If you were sampling features from the surface, for instance, or whatever method you have, 50 degrees is a lot of error. So we kind of went back to the drawing board to consider if there was another method that we could try to implement that might improve upon this even further. And I'm going to call this the ambiguity-free implementation of this neural network. The goal here is to just completely remove any of these additional errors based on the rotation estimate by removing the rotation estimation entirely. So instead of assigning some body axes based on the dimensions of the target spacecraft, we're going to instead just assign them instantaneously with each input to be parallel to the camera axes. So essentially what the network is now being asked to do is to just estimate the shape of the spacecraft relative to the camera axes relative to a set of axes parallel to the camera axes rather than its own body axes and a rotation of them. This is also a fairly straightforward implementation. Essentially what we do is during training, the set of points sampled from the ground truth shape model are rotated by that reference truth rotation, so that we feed into that chamfer loss function is just the rotated point cloud. And then the mask the binary mask that we generate during the reprojection calculations, this is no longer needs rotation incorporated into it because the rotation is simply just the identity matrix. So I have an example here of what I'm talking about. So if I were to give it this particular input image where we have this satellite that's at this angle, if this is the ground truth shape, I've taken the label that goes with that, the rotation estimate, reference truth rotation estimate, and I can sort of pre-rotate this reference truth shape before I feed that into the different loss functions. So this particular method gave us some other interesting results. So obviously we don't have a rotation estimate to compare here, but the chamfer distance, because it's exact, yes. But the chamfer distance was showing really similar performance to before. It's actually a little higher than what we saw with the ambiguity aware neural network, but it's much closer to it than to the baseline case. So I think this is about 17% of the baseline error magnitude that we saw an improvement by. And it seems to have a strong bias towards reproducing the reprojection accurately. So you can see in this particular example that I have here on the slide, the shape, sort of, if you look at the silhouette of the shape here, it's quite a close match to what you see in the reference truth. At the same time, it's a really strange assembly of shapes, right? It doesn't really resemble a satellite bus to the human eye. And we see kind of a even stranger cases sometimes in the test set. You can see here there's floating components and little balls floating around. So I want to emphasize that while we see this fairly strong performance compared to the baseline in this case, there's clearly a bit of tweaking to be done on this network still to try to encourage it to create those forms that you see a lot in those target spacecraft. Yeah, I'll figure out how to finish those thoughts in the final voice track. This slide is going to have a lovely animated figure that's going to show these assemblies that are going to be rotating, so you can see the different sides of it, and I can emphasize sort of what kinds of forms are being created, just like in my last thought. That's how I'll tie it to the last slide. So you can see in the summary of all the results comparing these two networks, the rotation errors were minimal, were less in the ambiguity aware case, but still a bit high for useful applications. The chamfer distance tended to be low in the baseline and the validation set because it tended to just simply memorize the alignments of those body axis triads. But when we're generalizing on unseen spacecraft, which is really the problem we care the most about here, we do see much stronger performance in both the ambiguity aware and ambiguity free cases. Most importantly, I would say the ambiguity free case has a lower chamfer loss than the baseline, and it doesn't couple in any additional rotational loss, so rotational error, that is. So this may be the superior approach to use when you're initializing some downstream process. So to conclude this work, we've demonstrated these two new implementations of a convolutional neural network that concurrently estimates the pose and shape of an unknown target spacecraft during rendezvous. The ambiguity-aware implementation reduced the chamfer distance error by about 20%, but we're still seeing a lot of really high rotation errors that would lead to challenges to use this in an actual navigation pipeline. On the other hand, this ambiguity-free implementation has comparable chamfer distance error, but it's got no additional rotation error coupled into it, so it may end up being the better choice to use. But I'll sort of caution the numerical results here with noting that these haven't been fully optimized, these implementations. So we really need to go tune the hyperparameters a bit further, see if we can kind of get better reconstructions of the shapes in that second implementation, for instance, or just see if we can sort of improve those metrics a bit more. And this should be happening concurrently with a larger training data set. The data set we're using right now is small. We're happy to have improved the performance a bit with the smaller data set, but we know that ultimately a lot more data is going to be needed to get really strong performance out of these networks. And then there's plenty more investigations we can do in the longer term down the road. So two really appealing applications for this is to initialize some sort of feature-based navigation and characterization pipeline, or initialize something like Gaussian splatting with this output. and skip some of those initialization processes that those have to do today. Another interesting idea that we've been thinking about is what if you use this output of the network directly as a measurement into a unscented Kalman filter or some similar sequential process? Is it a strong enough estimator to use on its own with sequential refinement thanks to a Kalman filter? This is really an unanswered question. We haven't tried it yet, but it may be a promising direction to go here and add to the list of options that you can use in a space debris rendezvous type of scenario. That concludes my slides. Thank you for listening. Give me all your feedback and advice.